Consumer Reports tested 14 randomly selected brands of vanilla yogurt and found the following number of calories per serving. We are asked to compute a 98% confidence interval for the average calorie content per serving of yogurt. Okay, so let's talk through our assumptions and just make sure we're not violating anything. Do we see the word random anywhere in the problem? And right up there in that first sentence, it tells us random. Do I see normal anywhere? Well, I don't. And I don't have enough of a sample, so we got 14 numbers. So I don't have a large enough sample that I can assume directly that it is in fact normal. So that means I need to go to a graph of some kind to confirm that it is in fact normal. So let's take out our calculator and do that. Okay, and I'm going to go to stat list or stat edit. So hit the stat button, then go to edit. And I'm going to go ahead and type in all those numbers. So 160, 200, 220. So I've gone ahead and done that ahead of time here. And what I want to confirm is I want to confirm that we're looking in fact at a normal model. Well, we can do that a couple of different ways. We can do it with a histogram or a box plot. That should be sufficient. So that'll be nice to kind of run through how to graph those different things. So I'm going to go to stat plot. Let's see what I've got it currently set at. Right now I've got it set at histogram, and I put my numbers in list 1, and I want frequency to be 1. Remember, frequency is how often does something occur, so I don't have anything, in my case, I don't have anything typed in for list 2 anyways, so I want to set that at list 1. And then once I've got all that switched up, then I want to hit zoom stat, so zoom 9, and it gives me that lovely picture there. Okay, now is that reasonable to assume that that particular graph is normal? Yeah, it looks pretty normal to me. So I could have done that graph, or, not and, but or, I could have also gone in and done a box plot. So if I go right back to stat plot and indicate that first box plot, because that first box plot will indicate if there's any outliers in it. So once I've got that selected, then I go back and hit zoom 9, so zoom stat, and I have a fairly normal box plot. I can see that my graph is trying to draw something at the bottom there, so apparently I've got some extra stuff typed in. But from the box plot I can tell it's normal. Normal meaning the tails are about the same width, and it is leaning more towards one side, but that's okay. It's more an issue of the tails and where it is in the middle of the rectangle. So this definitely appears to be a normal set of data. So it's normally distributed. And nowhere in the problem does it mention sigma, so I don't know the population standard deviation. So far we haven't violated any of our assumptions. We can go ahead and jump to the test menu. So I'm going to go back to test and look for a t interval. And this time I want to go data. So let me hit enter there. And in data, it's going to ask me, where do you have all this stuff? Well, all of my raw data is in list 1. Frequency would be 1 in this case, and I want a 98% confidence interval. So I'm going to hit calculate, and it's going to do some thinking, and it's going to tell me that the confidence level is between 126 and 189, and it actually also, in addition to, gives me the mean and the standard deviation of my particular sample. So the last thing that we need to do is set up some sort of conclusion sentence. So that would be, we are 98% confident that the true mean calorie content per serving of vanilla yogurt is between 126.16 and 189.56 calories. Okay, now let's kind of do a side question here. Diet Guide claims you'll get 120 calories from a serving of vanilla yogurt. Does our confidence interval match that it's around 120? So let me go back to where our numbers were. And our confidence interval was between 126 and 189. So that value of 120 is not in our confidence level, which means there isn't evidence to support 120 as a valid serving. Okay, so since 120 is not contained within the 98% confidence interval, the evidence suggests, doesn't promise, suggests that the average calories per serving does not equal 120 degrees. Okay. Now, just a quick note about confidence, because I understand 120 is less than the two numbers in our confidence interval, but confidence intervals cannot tell us what we call directionality. It can't tell us that in fact the real sample's got to be higher or lower than a given number. All it really tells us is whether or not something is equal to it. Okay. All right, the next thing that we need to address is how to find sample size. If we are asked to, if we're given a certain margin of error, a certain accuracy we'd like to have with our data, and the question is, well, how many people should we go out and sample? How large a sample size does one need? Well, the formula for margin of error is right now it's z star sigma divided by square root of n. And you're thinking, wait a second, we just did t stars, what's going on? Well, now we're talking about sample size. So we've sort of changed the question up, and we'll go through an example on that. Just a reminder, when we're calculating sample size, we always want to round up. Okay, so we are told that the heights of male students in a particular population is 2.5 inches. So in other words, before we go out and collect data, we think it's 2.5. The question is, how large a sample does one have to be in order to be within 0.75 inches in that 95% confidence level? Okay. So I'm going to have to type up that formula and then take a look at sorry, I'm hitting buttons here. So I'm going to have to take a look at this particular confidence level. Okay, so we are told that the margin of error is 0.75, and I need a z star for 95%, so that's 1.96. They tell me that sigma is 2.5, and I want the square root of n, so I'm eventually going to solve for n here. Okay, so what am I going to do first? I'm going to divide 0.75 by 1.96. 0.75 divided by 1.96, and that's going to equal that fraction there of 2.5 divided by the square root of n. Okay, then I want to rearrange this so that I can solve for n. So I'm going to sort of cross multiply here. So 0.75 times the square root of n equals 2.5 times 0.96, and then I want to divide by the 0.75. So that leaves me with the square root of n equals, I'm going to talk through the fraction here, 2.5 times 1.96, and I want to divide that by 0.75. And then the last thing is to get n, so n would be that whole fraction squared. So I'm just going to copy and paste this in. And I want to square that. Okay, so now I'm going to go to the calculator and type in all that information. So I want 2.5 times 1.96 divided by 0.75, and then I want to square that. So I get a sample size of 42.68, but when you're talking about sample size, you want to round up. So that means I want to talk to 43 individuals, and then I would be able to have an accuracy of that plus or minus 0.75. Okay, so 43 people. Okay, and so lastly, a couple of cautions about this student T process, and just to be aware of. In order for this to accurately describe, in order for us to make a valid conclusion, we do have to either be told it's an SRS or reasonable to assume it's an SRS. As you go into, if you happen to go on to further statistics courses, the formulas get actually more complicated, and there's no way to correct for bias in data. Outliers can have a huge impact on confidence intervals, and it's nice if we happen to know sigma, then our T process turns into a Z process. But you know, as I've tried to say several times, it's not really realistic to think that we're going to know what the standard deviation of the population is, considering we're trying to estimate what the population is thinking.